Okay, so Chem 50 review here. So let's just start with the basics, which is obviously units, right? And when we talk about units, whenever you take a measurement, there should always be a number and a unit associated with it. And that's a problem for a lot of people. And that's because, again, if you just have a number like 150, who knows what I'm talking about, right? So I could be talking about $150, which would be great. You could talk about 150 pennies, would still be great, I think. 150 apples, still great if you're making some pies, maybe, or something like that. But really, without the unit, there is no sort of correlation to what that number represents. It's just a number, right? So if this is 150 apples, then I know I can make a lot of pies, right? And I know what I'm talking about. I know what I'm referring to. So you should always get into a habit, and hopefully you have those habits from previous classes, that whenever you have any type of measurement, there should always be some type of unit associated with it. Definitely in your notebook, right? As you're recording values, you should record values to the proper digits, the proper units along the way. As you may be familiar with, right, there's two types of units, sometimes referred to as the US units or English units, and then pretty much everybody else in the world uses the metric system, right? And along in 1960, they had a conference on weights and measures, sounds like fun. And they came up with that other kind of unit of measurement that you commonly see in chemistry, which is known as the SI unit of measurement, which is an international system of units. Let's be honest, it's the metric system, right? It's pretty much what it is. So we do have some different units, and it's important as we do conversions between these units that we understand, the difference between that, right? So the common one, right, between those is 1 inch is exactly 2.54 centimeters, right? So if you had a ruler at 1 inch and you go down, that's basically 2.54 centimeters on the bottom of a ruler. By the way, on the top right are inches on a ruler, right? On the bottom are typically centimeters, right, that have numbers. The little guys on the bottom that don't have numbers before the centimeter are millimeters. Yeah, so those are millimeters there along the way. So let's talk a little bit about taking sort of proper measurements. And actually, before we do that, let's talk about sort of some very important things that people screw up on. Speaking of units and metrics, a lot of times we have prefixes, right, that we use, especially with the metric system. Like kilo is 10 to the 3, right? And maybe centi is 10 to the minus 2. And when we look at these and use these as conversion factors, people oftentimes will do these incorrectly. So, for example, when we see something like this, first off, that really is 1 times 10 to the 3 in scientific notation, right? And what that is how much there are in the base unit to one of the prefix units. So, in 1 kilometer, which is a prefix unit, there would be 10 to the 3 meters, which is your base unit. And that is the proper way to do that. Most people do it backwards. They go like 10 to the 3 kilometers is like 1 meter, and they always sort of get it incorrect. It doesn't really matter what the base unit is, right? 1 kilogram is 10 to the 3 grams. 1 centimeter is 10 to the minus 2 meters. Sometimes you maybe have learned the bigger numbers, which you get when you divide 10 to the minus 2 to both sides, right? And then you end up with 100 centimeters is 1 meter, right? Same conversion. So I would say that's a super common error people always want to make, is they always kind of want to use those prefixes that are commonly used sort of backwards. So just make sure you don't do that. So when you see that, that's how much there is in the base unit to one of the prefix units always. Now, speaking of measurements, as you may know, right, with any type of measurement, there is a certain amount of uncertainty associated with it. So no matter what type of measurement you take, depending on the piece of equipment that you use, there will be some uncertainty, some estimation that has to happen. And that is what happens with a measured number, right? With a measured number, you have some type of estimation that happens. That is different than, say, an exact number that you might remember. An exact number is something that is counted, or a definition, like 12 inches equals 1 foot, right? That's an exact number. If I had 4 apples on the table, I would just count them. I'm not going to do any type of experiment to figure out how many I have. Those are exact numbers. But whenever you take a measurement, that is a measured number, and that has some important aspects of it. So if we take a look here, I'll call that a 1. Let's say we did have a ruler here. Let's say these are centimeters. And let's say we wanted to measure this arrow. Whenever you're taking any type of measurement, which is really the topic of the first experiment we're doing starting on Thursday, you always want to look for really two things on the scale. They're sometimes referred to as large markings. And large markings typically have the actual numbers written there. So in this case, that's a 1, and that is a 2. The difference between that is 1 centimeter difference, right, between those two large markings. Now, typically, you also have small markings. And the small markings are the ones that come between the large markings, and they don't usually have any type of numbers associated with them. It's important when you count correctly, which is you start counting after the last large marking, and you continue to the next large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and you stop here at the next large marking. That's going to be 10. So there are 10 markings in between the 1 centimeter. That means each of the small markings represents how much? 1 divided by 10 is 0.1. Oops, come here. 0.1 centimeters, right? So this would be 1.1, right? 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. So when we look at anything that we're measuring, there should always be numbers that pretty much everybody should agree upon. So everybody looking at my arrow should hopefully agree it is at least 1.3, right? It's definitely at least 1.3. In this case, though, it's not exactly 1.3. It's not exactly 1.4. It's somewhere in between. And that is where the estimation comes into play, and that's where the uncertainty comes into play. These are sometimes referred to as all the certain numbers. Now, when I look at that, to me, perhaps it looks like it's dead center. Other people may look like maybe it's going a little bit more to the right or a little less than center. So I may call it a 5. Somebody else may call it a 6 there at the end. It really doesn't matter. And we would record centimeters as well. This is what is known as the first uncertain number. And whenever you take a measurement, you should always record all the certain numbers plus the first uncertain number. The reason we do that is when you do that, that makes everybody's favorite things, which are significant figures. Yeah. So this number here would have how many significant figures? It would have 3 significant figures. Yeah. So it's really important to record all those values because that gives you the proper number of significant figures when you take a measurement. Any questions on that there? Now, it does depend on the scale that you're using. Obviously, if I took something like a terribly drawn graduated cylinder, and it's not too bad, I guess. I'll go 10, 20, a little milliliter action. We'll put a little volume in there, maybe. When we have liquid in a glass container, typically exaggerated drawn here, right? We get the curvature of the liquid, which is known as the meniscus, right? And that occurs because of the attractive forces, right? Cohesive and adhesive forces. The attractive forces between the liquid and the glass is stronger than the liquid in itself. So those on the outside that's touching the glass go upwards through capillary action, so it rises. That is why we take the reading from the bottom of the meniscus when it's a U-shaped type of meniscus. And that's because in the middle there, there's no attraction to the glass. So that is actually where the liquid is, right? It's not the sort of exaggerated upward pull that you get on the sides because of that attraction. Most things do have a U type of meniscus. Only few things have a meniscus that actually goes the other way. Looks like that. Mercury is a very common example of that, which you will not see because it's mercury and they took it out of the labs in schools for a long time ago. But mercury actually goes the opposite way, and that's because mercury is actually more attracted to itself than the glass, so it actually comes in on itself and goes downward rather than going upwards. And in this case, you would actually read from the top of the meniscus because it's upside down. So if you have a U-shaped meniscus, which mostly is what you will have, you typically read from the bottom meniscus, but it can go in the opposite direction depending on what the solution is. So same idea here. We're going to look at our large markings, and our large markings, that's a 10, that's a 20. The difference between that is 10 milliliters. Once again, counting our numbers there on our scale, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So we have 10 small markings. So each of the small markings in this case, we just divide that by 10, means that each small marking is 1 milliliter. That would be 11, 12, 13, 14, 15, 16, 17, 18, squeezing 19 in there. And if I sadly draw a straightish line there at my meniscus, I'll put it right there. We can see in this case, it is at least 13. So I do not record those, which is by certain numbers. Once again here, it's not exactly at 13, not exactly at 14. Maybe I feel it's a little bit further up this time. 0.7 milliliters being my first uncertain number. And that again is going to give me 3 significant figures, as all of these guys here are going to be significant. Now, again, you may be using the exact same piece of glassware, but maybe it was made by a different company. And what happens is, let's say we had this, bless you, come up there, and we'll go. There's, and we'll pop our liquid right about there, maybe. Now, when we look at this one, large markings here for this particular one, still 10 milliliters. But when we count up our markings between, we got 1, 2, 3, 4, and 5. And since there's only 5 markings, how much does each small marking represent in this case? 2 milliliters, right? So this would be 12, 14, 16, 18. Now, when I take a reading here, I am actually between 14 and 15, which means, I'm sorry, 14 and 16. And the number between 14 and 16 is 15. And that would be the best you could do in this particular case, which would mean it has how many significant figures? 2. And the uncertain number is the 5, right? So you're basically saying, I think it's 15, but maybe it's 16, maybe it's 14. Not the greatest measurement per se. The reason you cannot go any further is between 14 and 16, you have no idea where 14 ends and 15 starts, right? So there's no way for you to kind of figure that out. And that's the best you can do. So it does depend on the piece of equipment. Now, typically speaking, if you're not sure how far you could take the reading to, but you are confident in what the smallest markings represent, you typically can go one more place to the right of the smallest markings. If you are, again, confident on what the smallest markings represent, but you're not exactly confident how far you should take it, you could actually just always take the smallest markings and divide it by 2. So if I did that, that is 0.05 centimeters. That is 2 decimal places, which is exactly where I should take the reading to. If you come over here to this one, 1 milliliter divided by 2 is 0.5 milliliters. That is 1 decimal place, and that is where I took my reading to. Even works for this weird one. Take the 2 divided by 2, which is 1 milliliter. That's a whole number, which is where I took my number 2. So if you're unsure, but you are sure about the smallest markings, just divide it by 2. And however far that number goes to when you divide it by 2 is how far you should take the reading to. Any questions on that? That's sometimes referred to as the tolerance in the measurement. You may see like plus or minus a number after a measurement. That's how you get that plus or minus part, by dividing the smallest marking by 2. And for example, you would say if you're going to put that in there, this is 13.7 milliliters plus or minus 0.5 milliliters. Basically, that's where that comes from. We usually don't at this school include that. We just want to make sure we include, obviously, the right amount in terms of our sig figs. The other really important thing is I know how perfect everybody is in this class, especially when they're taking measurements, right? And you sit in that balance room all day, taking out every little crystal you can to get it exactly on the nose, right? Exactly on the number. Nobody believes that, by the way, just so you know. So let's say my arrow here is right there, exactly at the 1.4. And obviously we could go through our little parts here and get our correct markings. So we record 1.4 centimeters, 1.40 centimeters, 1.400000 centimeters. Doesn't matter how you record it. It does matter, right? So let's just start with this one. This number written like that has how many significant figures? Has 2. The uncertain number is the 4, right? So when you record this as 1.4 centimeters, you're saying, I think it's 1.4. And maybe it's 1.5. Maybe it's as low as 1.3. That's uncertainty in that last digit. So you're basically saying, I think my measurement based on the scale I got going on, it's somewhere in this ballpark. That's a lot of error. Yes, that's a lot of like, I'm not sure where I'm at, right? So by lofting off a number, you actually now are making your measurement really, really worse. 1.40 has how many significant figures? It does have 3 sig figs. The estimated number is at 0. So when you record 1.40 centimeters, you're saying, I think it's 1.40, maybe it's 1.41, maybe it's 1.39. That is now an error of like in this area, right? Which is what you can actually do on this piece of equipment. So even though you got your arrow to line up perfectly with that dash and you took an hour to do so, you still need to record it with the 0 to maintain the proper number of significant figures. Otherwise, like I said before, if you recorded this guy, you made your measurement pretty crappy. Yeah, a lot crappier than it should be based on the equipment that you have. Now, it also goes with this, right? This has how many significant figures? That last one. I don't even know. I just was writing zeros. So we got 3, 4, 5, 6, 7. It's got 7 sig figs. That means that the uncertainty is way out here, right? There's no way you could get that uncertainty on that piece of equipment, right? So by adding extra zeros to make it look more chemistry-like, you're actually telling people you made a better measurement than you could ever do with that piece of equipment, and you shouldn't do that either, right? So sometimes we do need to add a 0 to maintain the proper number of significant figures if you get right to the right line. You definitely don't want to drop significant figures because it's really, really important. By the way, when we record something that is in a digital format, we always record all the numbers there as they are all important. So you should always record all the numbers that are, for example, on the balance, the mass. You should always record all those numbers. Any questions on that there? So obviously, talk about here are sig figs, just officially, right? All non-zero numbers, right, are significant. So if you had 1, 2, 3 creative numbering there, that is 3 sig figs. We always start counting left to right, right? We're counting significant figures. We do not start counting significant figures, right, until we hit the first non-zero, right? So that is what we do there. Speaking of zeros, those are the ones that give people trouble. We have leading zeros, which are not significant. And those are zeros that come before the first non-zero number. So none of these zeros are significant. we don't start counting until this one, and then the rest of them would be significant. So that is 4 significant figures in this particular number. They're sometimes referred to as trap zeros or captive zeros. Those are significant, and those are zeros that are between two non-zero numbers. So we would start counting our sig figs there. These zeros are traps, so they're significant. That's significant. That's 4 significant figures. Lastly, the zero that gives people the hardest time is the trailing zeros. And those may or may not be significant. And what determines if they are significant is if there is a decimal point written in the number. So it has to be actually written number for those zeros at the end to be significant. So if I had 400 like so, it has how many significant figures? It has 1 significant figure. This is the only one that is significant. If I wrote 400 like so, it now has 3 significant figures with the decimal point there. Makes this zeros at the end significant of a 0.00404030. How many significant figures? Did I do 7 again? That's not bad. I want to say. So we don't start counting until we hit this one. Significant zero, significant is trap, significant trap zero, significant, significant, and these zeros at the end are going to be significant because way over there there's a decimal written. So 1, 2, 3, 4, 5, 6, and 7 again. Yeah. Any questions on counting significant figures? Now, when we use significant figures in calculations, right, we want to always give our answers to the proper numbers, significant figures. And the two types of calculations that we do is we multiply or divide. And when we multiply and divide, we look at the number of sig figs. And it is the least number of sig figs your answer should have. So if I took 32.5 times 1.2 and we're multiplying, this guy has 3 significant figures. This one has 2 significant figures. Our answer should end up with 2 significant figures. When we subtract or add, we look at decimal places. And it is the least number of decimal places. So if I was adding 4.256 plus 1.11 plus 3.0, we'll try without the calculator, 663.478, right? So this has 3 decimal places, 2 decimal places, 1 decimal place. We would end up here because that is above 5, right? We would round up, giving us 8.4, right? 8.4 has 1 decimal place, but has 2 significant figures. And that's important in case you took that number and was going to go on and do some other type of calculation with it. Any questions on that? You do need to keep track of all your sig figs as you go through the calculations. So if you're doing some type of combo deal, you got to kind of figure it out. Yeah. Okay, so yeah, so for example, if we were doing something like this, then we're gonna have plus like 1.1113. Here we were multiplying, so we would look at sig figs, and obviously based on what was in the parentheses, we would do that first. So that's gonna be 3 sig figs on top. Next, we would take the top number divided by the bottom. So that's 3 sig figs divided by 2 sig figs. Technically, our answer that we would get here would be 2 significant figures for everything that's on the left-hand side. Now, should you round at this point? You should avoid rounding usually until the very end, right? So you should just keep track of everything and you should maybe avoid rounding. So if I actually do this made up numbers here, I end up with like a big old number there, 85970.2381. plus now 1.113. At this point, I do need to switch back to adding and decimal places. Now, since this should have two significant figures, that is here, right? Which means really we should round. By the way, if I round that number, what number do I get? 80, is it 86? Not 86, right? Because that changes the meaning of the number, right? That original number is 85,970. So just as an example, if I owed you $85,970, I said I'm going to pay you two significant figures. Here's 86 bucks. Am I good? Probably not gonna make it out the door. Maybe I will. You guys look nice. You look like maybe I'll get out the door with that. But no, there's really obviously a big difference in those meanings. This is a case where if we were going to end the number here, we would have to round that to something like this, right? 86,000 still has two significant figures, still maintains the meaning of the number. I would not want to put a decimal really at the end because now it has five significant figures, right? So that technically would be it. But basically, the importance of that is now that I'm adding here, I have to look not at significant figures, but look at decimal places. And really, based on where this number should end, it has no decimal places. This has four decimal places. So my answer actually should end up in this case as a whole number, right? Is what my answer should end up with along the way. So it's really important as you go through the calculation that you keep track of it. Sometimes people are taught to put little lines over things or whatever you want to do. I would again highly recommend not rounding too much, or at least keep what's sometimes referred to as guard digits and a few extra digits, more than where you should be rounding it off to. And you should be okay, so you don't have any type of rounding error and stuff like that. You definitely, again, don't want to do any extreme rounding. I mean, that's also a very common error people make is like they try to get the right sig figs. So they round it off and they change the meaning of the number. And you definitely don't want to ever do that. Any questions on that? Now, scientific notation is used a lot, right? And that is a number written as n times 10 to the n. That is a number between 1 and 10. It cannot usually be 10, and it can't be less than 1, but it can be 1. But it needs to be somewhere in there. Times 10 to this little n is either going to be positive or negative, depending on which way you need to move the decimal point to get to a number between 1 and 10. So if I had 1425, we assume the decimal point's here. So 1, 2, and 3 places gives me 1.425 times 10 to the 1, 2, 3. Large numbers typically have positive exponents. So move it to the left there, gets you that. If I had 0.0032, 0, we got to go one place, that's 0.0. One more place is 0.3, that is not 1. One more place is where we need to go. We end up with 3.20 times 10 to the minus 3 in this case. We keep the 0 in that case because when you take a number from regular form there, decimal form to scientific notation, you should not lose any significant figures along the way, right? So this one has 4, which is why we kept all of them. This one has 3, which is why we kept all 3 of them. By the way, when you write a number like so in scientific notation, all the numbers before the times 10 part are significant figures. So these are all sig figs before the times 10 part. There can sometimes be only one way to write a number with the correct number of significant figures, which is to write it in scientific notation. Because in scientific notation, you could kind of control how many significant figures you have. If I needed 2 significant figures for a number like so, that would be 2. If I needed 3, now I have 3, right? If I needed 4, perhaps now I have 4. So you could kind of control how many significant figures you have in scientific notation, and sometimes that is the only way to get a number to the right number of sig figs. Question on that there. Probably more important than any of that is to make sure you know how to actually use scientific notation on your calculator. Yeah, and that is really important. So when we're doing scientific notation on your calculator, your calculator should have an exponent button. It looks like EE. It should have an EXP button. And some of the, I guess they're not so new anymore, but kind of like the two-tone calculators where there's like a color, main color, and like the sides are a different color, will have actually a times 10 to the n. Typically, these type of calculators will also have like a little will sort of thing happening on your calculator. And these are your exponent buttons that you want to use when you're doing scientific notation on your calculator. Also, most calculators have a negative button or change the sign button that looks like that. R looks like this, not the subtract button. And when you put a number into your calculator, we'll start with these two buttons here. If you want to write 1.25 times 10 to the negative 4 and actually punch it in correctly, you should go 1.25. You then should hit your exponent button. On your calculator, probably will display 1.25, may put an E, may go 1.25 and pop up a couple of zeros, may do like a 1.25, a small times 10 on the bottom, pop up a couple of zeros. When you hit this actual button, the exponent button, it represents this part of the number, which means you should not be using the multiplication button or anything else. You have only the negative 4 left in this example that you have to push. And at that point, what you would do is hit your negative button and 4. It will put a negative 4 there, pop that into a negative 4, pop that into a negative 4. And that is the proper way to punch it into your calculator. Now, if you have this calculator, which again is kind of like a two-tone sort of calculator, you have to do a little extra work, and it's okay. You have to put every number that's in scientific notation in parentheses. Otherwise, your calculator will do the math incorrectly. So if you were doing this exact same number, if you had that calculator here, you would have to open up a parentheses and do 1.25, hit your exponent button, times 10 to the n. On your calculator, what you'll see is parentheses 1.25 will pop a times 10, and you'll have a little blinking cursor kind of blinking right up there at the top. At that point, you could kind of do the rest. You could hit your negative button and 4, and then you will end up with a 1.25 times 10 to the negative 4 with the little blinker guy to the right of it. Now, if you go to close the parentheses at this point, you're going to get a really small parentheses up on top and probably an error message on your calculator because it's not going to like that. So what you have to do is use the will and hit the right-hand side of the will. That will bring your little cursor down to regular size, and then you could close the parentheses, and then you'll have a number that looks something like this, and now you're in business. So looks like a lot of steps, but if you know how to do it, it goes obviously really quickly and stuff like that. And these are the proper ways that you should be putting numbers in your calculator in scientific notation. You should absolutely never use the shift log, inverse log, second function, and log because you're doing it incorrectly. You will sometimes get lucky, but a lot of times in this class, you will not get lucky because then we'll be using the actual log function with that number. And now you kind of screwed up your number because you put it in incorrectly. So it's really important to make sure you know how to do that. If you find yourself at times getting what looks like the right answer, but the exponent is incorrect, you probably punched it in incorrectly, and that's usually very common. It's usually super close, and even the exponent's really close. But if you're off, it's usually how you're punching it in. Any questions on how to use your exponent button? Again, if you're not sure, just let me know, and we could probably find it on your calculator specifically. All right. Speaking of that, right, there's a difference between accuracy and precision. So when we talk about accuracy versus precision, accuracy is how close you are to the right value or true value, I guess is the better way of putting that. Precision is how close a set of numbers are to one another. So the classic example is throwing darts, right, at a sort of bullseye. The goal is to get the darts at the bullseye, right? So if I throw my darts and I hit here, I hit over here and miss the board, that's not bad good. Am I precise? I am not. I'm all over the place. And I probably just stuck somebody with a little dart. Am I accurate? I am not accurate because, frankly, I'm trying to get the bullseye. So I pick up my pride and my darts and I go double or nothing. And I throw my darts again and I go boom, boom, boom. Am I precise? Am I accurate? Yes, I'm precisely not accurate. And you can be very precise and do the experiment, for example, wrong every time the same way and get the same answer, but it's still wrong, right? So you can be very precise at doing something, but if you're doing it wrong every time, it's still not very accurate, right? So I'm getting better. I kept them all on the board there. I go triple or nothing. You shouldn't gamble, obviously, right? And I throw my darts and I hit boom, boom, boom. Am I precise? Am I accurate? Yeah, and that's what we're shooting for, right, in chemistry. And obviously, when you're doing experiments, you want to be accurate, which means you want to kind of get the right answer. You also want to be precise. And how we look at precision in the lab, right, is we do multiple trials, right? So we do multiple trials of the same experiment to see if something is reproducible, right? The reproducibility of the experiment. And that's the goal of that. For accuracy, we oftentimes look at something like percent error, which is your experimental value minus the true value divided by the true value times 100%. Do I want a high percent error or low percent error? You do want a low percent error, right? Percent yield, you like a high one. Percent error, you want actually a low one, right? Now, for precision, we look sometimes at standard deviation, right? Um, our percent deviation is what we sort of look at as a measurement of reproducibility. And these are things that you'll have to calculate in certain labs, some standard deviation, percent deviation, percent error. So earlier when we saw that sort of lab manual introductory pages, again, in those pages are a lot of information on how to calculate those type of things as well. Any questions on that there? All right. We use equalities like 12 inches equals 1 foot to give us conversion factors, which are fractions, right? So we can write two conversion factors. And that's an equality. An equality is two measurements or two values that represent the same amount of something, but are on different units, right? So 12 inches is the same distance as 1 foot. 100 pennies is the same amount of money as $1, right? So they're just on different units. We show our work in chemistry by everybody's favorite thing, which is dimensional analysis. Dimensional analysis is where we kind of show the units canceling out by using conversion factors. Bless you. So if I had 4 inches and I wanted feet, we would show it something like this. Kind of opposites cancel. So although it's not written as a fraction, the units of inches are up on top. To cancel it out, we would need to use a conversion factor where the units are in the opposite location, which is 1 foot, 12 inches. Math-wise, whenever you do dimensional analysis, whatever's up on top gets multiplied, whatever's on the bottom gets divided. That is how the units cancel out because you're essentially taking inches on top and dividing it by inches on the bottom, which gives you 1 and they cancel out. Same thing if you took 2 divided by 2, it equals 1 as well, right? And that's why opposites cancel out the units. And in this case, we would multiply there and end up with our 4 divided by 12 there, a 0.333, lots of threes here. These units cancel. That is the only unit left. If we're solving for 1 unit, it should usually be on top by itself. You can't have 2 units that you're solving for. Sig fig wise, right? These are considered exact numbers, which means you do not need to worry about those in your calculations, right? And usually conversion factors are, if it is between English and English conversions, metric and metric conversions. The only time you have to worry about a conversion factor, right, is when you cross over from English to metric or vice versa. The only one you don't have to worry about is the 1 inch equals 2.54 centimeters. That's an exact conversion. That means sig fig wise, we would look at our original number, which has two significant figures. That's going to take us to there, and we should clean this up to 0.33 feet, right? Now, you should show your work with dimensional analysis in a lot of cases when you're doing some type of conversion. It also can be very helpful for you if you can't remember a formula. You could just think of it like a dimensional analysis problem, get rid of the units you don't need, keep the units you do need, and it will actually do the formula for you. And because you're always doing multiplying and dividing here, you're always looking at sig figs at the end in terms of your answer. You're doing a multiple step dimensional analysis problem, our calculation in general, people get in trouble by trying to put too much into their calculator at once. So if you have multiple numbers on top that you need to multiply, you can multiply as many numbers as you like on top. At the end, you should hit equals. If you have a bunch of numbers on the bottom you need to divide by, you should divide by the first number, hit equals, divide by the second number, hit equals, divide by the third number, hit equals, and you will always get the right answer. You try to put all that in at once, most people don't use parentheses correctly on their calculator, and they end up with the wrong answer. So that's always a good idea to always use the equal button multiple times throughout the calculation, and you'll usually get the right answer if you're doing that. Any questions on dimensional analysis there? All right. So obviously, nomenclature, right? Bless you. We should know how to name things and what things are. That way, when we read instructions for our experiments, we grab the right stuff. So first off, right, there's ionic compounds. Ion compounds are made up of our friend, the metal and the non-metal, right? Always an ionic compound if you have that combination. Also because of periodic trends, things like ionization energy, electronegativity, electron affinity. When those two guys get together, you get a transfer of electrons, right? From the metal to the non-metal. That's what creates a cation, which is positively charged from the metal, and the anion, which is negatively charged from the non-metal. What holds that together is the electrostatic attraction between the positive and negative charge. There is no sharing of electrons in an ionic compound. That is different than a molecular compound, or sometimes referred to as a covalent compound that has covalent bonds. That is two nonmetals. And when you get two nonmetals together, because they're the same spot on the periodic table, they have similar properties, which is neither one of them want to get rid of their electrons, right? They want to hang on to their electrons because as we go up and right on the periodic table, fluorine is the most electronegative atom you can have. And because of that, the best that they will do is they will decide to share electrons, right? Creating a covalent bond. So we will have sharing of electrons here. Could create a polar covalent bond, which is unequal sharing of electrons based on electronegativity difference. Could create a non-polar covalent bond, which is equal sharing of electrons. Perhaps you did some difference in electronegativity values using Pauline's values of 0 to 4. Yeah. Right now, yes. And it creates some different types of bonds. This is also important because that is the basis of naming as well, right? Depending on whether it's an ionic compound versus a molecular compound as to how you name it. And when we name things in terms of ionic compounds, there's type 1 ionic compounds. Type 1 is the metal has a fixed positive charge. And as you hopefully know from the periodic table, those are our metals in group number 1, 2, 3. Zinc, cadmium, or silver. All those have fixed positive charges. So when you roll with something like this, that's a metal, that's a non-metal, tells me it's ionic. Metal is always the most important thing. That is group 1, which means it's type 1. That means we call this sodium oxide. Do we use prefixes with ionic compounds? No. Yeah. So prefixes are never used when a metal's involved. So if there's a metal, you should never use it. Type 2 ionic compounds are metals that have variable charges. Those are typically your transition metals, which are between groups 2 and 3 on the periodic table. And also just to the right, under the staircase, where you have things like lead and tin located. Those have variable types of charges, which means when we have something like that, FeCl2, the metal can have a variable charge because this is a transition metal. So in this particular case, not sure what the charge is, but I knew chlorine is group 7, has a -1 charge, and that's a -2. Whenever you put a positive ion, negative ion together in an ionic compound, the overall charge needs to equal 0, right? And that means that the iron here would have a +2 charge to balance it out. That would give you iron Roman numeral 2 for the charge. And this would still be chloride, still no prefix in this name. The Roman numeral indicates the positive charge on one of the metals and not how many metals that you have. Question on that there. Now, type 3 compounds are covalent, are molecular, and that's our sharing of electrons. That's our two nonmetals together. And that is where we actually use prefixes. So this is the place where we use prefixes. We got mono for 1, right? Di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, deca for 10. I'm going to stop there, I think. Now, when we use these, we don't have to worry about charges or anything like that because there's no ions involved. They are sharing electrons. So we just need to pick the appropriate prefix. So we'll use this demonstration here to demonstrate all the things we should not do. First off, we have 1 carbon, which is a nonmetal. Oxygen is a nonmetal. That is 2 nonmetals, which tells you it's type 3. Prefix for 1 carbon is mono. And the one thing that we do not do is use mono on the first name. So that is the only prefix that we cannot use on the first name. But it is okay on the second name. So it's okay on the second name. So because we cannot use the prefix, we just use the whole name of the first element, which is carbon. We do have one of the second one, so we can use mono here. And the second element gets the IDE treatment at the end of it, and that's monoxide. Now, typically what happens in type 3, as you might remember, is you will sometimes get 2 vowels that back up to each other like we do here, 2 O's or an A and an O. We typically get rid of the vowel from the prefix, and instead of carbon monoxide, this is carbon monoxide, right? Would be the proper one, right? N2O4 dinitrogen tetroxide here, right? So dinitrogen. Again, this is typically tetra, but we have an O happening there after the A, so we're going to get rid of the A, and this would be oxide at the end there in that case. Question on type 3 there. Right. Then we obviously have everybody's favorite thing, polyatomic ions, right? And polyatomic ions end in either ate or ite, most of them. The difference is the number of oxygens that it has. They have the same charge. So if you have SO4 2 minus or SO3 2 minus, the one with more oxygens ends in 8, like you ate too much. That is sulfate. Least oxygens, that is sulfite. Also, we sometimes have groupings of 4 together, right? ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. They all have the same charge. They are all held together by sharing of electrons. The only difference is the number of oxygens. The one with the least number of oxygens, we put hypo at the beginning, and then we do ite at the end. I won't do the 2 middle. They're just like this. That is chlorite and chlorate. And then the one with the most oxygens has per in front and 8 at the end. So that is perchlorate. in that particular case. So perchlorate on the right, chlorate next, chlorite, and hypochlorite. For the most part, as you might remember, right, most of the time polyatomic ions are hooked up with metals. And we fall back to our same type 1 and type 2 rules. Either use a Roman numeral or no Roman numeral, depending on the metal that is present with those. Also, if you have more than one polyatomic ion, right, you need to put parentheses around it and a number on the bottom to indicate how many there are. So you don't end up with a formula. Actually, let's do this. So you don't end up with a formula that looks like this, right? So the difference obviously is I do not have 33 oxygens, right? So that's no good. So because I have 3 of the nitrate units, I do have to put parentheses around it and the number on the bottom there to have the right formula. Important for our class in terms of nomenclature, acids, right? So to name acids, a reminder that it all involves whether or not there's oxygen. So if the answer is no oxygen, your acid starts with hydro and ends with ic acid. So HCl, and those are typically aqueous. HCl is hydrochloric acid. Now, if it does have oxygen, and the answer is yes, it has oxygen, it will probably have a polyatomic ion. And as we just talked about, that will either end in 8 or it will probably end in ite. And if your polyatomic ion ends in 8, your acid will end in something ic acid, like HNO3, aqueous symbol. NO3 is nitrate, so this will be nitric acid. If it ends in ite, your acid will be OUS acid. So HNO2, that is nitrite. This would be nitrous acid. H plus, right, is the cation for all acids, right? So the negative part is on there. Any questions on amino acids there? Go. Now, we obviously have equations, and we always balance equations when we have them. And we have types of reactions, right? And when we talk about types of reactions, they're really broken up into 2 categories: redox reactions and double displacement reactions. And as I mentioned earlier, for us in this class, we do see a lot of double displacement reactions. We will see some redox reactions later on in the semester when we get into electrochemistry, but a lot up front is a lot of double displacement reactions. Redox reactions means that you are oxidation occurring, right? And you lose electrons. Reduction, you gain electrons. Underneath redox reactions, there are more specific ways to classify them. That is your synthesis reaction is a redox reaction. That's your A plus B makes 2 things make 1 thing. Your decomposition reaction, 1 thing breaks apart into 2 things. Your single replacement reaction, 1 thing with no charge reacts with something that's ionic, comes in and kicks it out, and that will make a new ionic compound. And the guy that gets kicked out will come out with no charge. In order for that reaction to happen, whatever is coming in needs to be more reactive than what it's replacing. Otherwise, it will not happen, like an activity series. Maybe we did that in Chem 50. Also, combustion reactions. Really, the only thing that you need for a combustion reaction in the equation is oxygen, and technically it's a combustion reaction. But most people will think about the organic combustion, like when you light a Bunsen burner, plus O2 will make CO2 and water. So all these are more specific ways to classify reactions. On the left, they are all really redox reactions that are occurring. Double displacement reactions is another classification of reactions where you have 2 ionic compounds. It is the only reaction where 2 ionic compounds come together. They always switch partners and make new ionic compounds on the other side. And you may recognize these reactions by their more common names, which is your precipitation reaction, where that double exchange makes a solid or a precipitate is formed, or an acid-base reaction, which we will see a ton of in this class, where you will typically make water, right? And these are the three reasons why reactions take place, as you may remember, or if you don't know, these are the three reasons why all reactions take place. Either you made a solid, you formed water, or you transferred an electron. Those are the three reasons why reactions take place, and they are under these two classifications of reactions. So it's, again, really important to know that. I would say definitely review the double displacement because, again, we see a lot of that in here. And being able to write your reactions correctly is really important. When you have an equation right on the left-hand side are our reactants, they go to our products. We always balance the equation by using coefficients to do so. So when we have a reaction, we only change the numbers in front. So we will put a 2 there. We will put a 3 there. These coefficients are the only things that we change. These are also really important because in stoichiometry, when we're doing calculations, these are the mole to mole relationships, right? As each of those can be represented as moles, we could say 1 mole of nitrogen reacts to give us 3 moles of H2. 3 moles of H2 will give us 2 moles of NH3. 1 mole of N2 will also give us 2 moles of NH3. We could use these as conversion factors to do stoichiometry problems, right? And we also sometimes have limiting reagent problems. Limiting reagents and excess reagents are important. The limiting reagent is always the one that determines how much product you make, right? And so the limiting reagent or reactant is what determines how much product you make. And that sometimes leads you to your percent yield, right? Which is your actual yield divided by your theoretical yield times 100%. Your theoretical yield is your maximum yield that you could get in an experiment based on the stoichiometry and the amount that you are starting with. Your actual yield is actually what you get when you do the experiment. Percent yield, we do look for a large number. We also usually have the excess reagent, right? A reactant, and you have some of that left over at the end of the reaction. So you still have that present, right? In order to do some important conversions in stoichiometry sort of calculations, in addition to some other calculations, we use molar mass from the periodic table, right? Molar mass is our conversion factor. When we look at the periodic table, that is the number on the bottom. We typically go 4 significant figures when we pull it off there. And that means for carbon, there's 12.01 grams per mole that we could use as a conversion factor, 12.01 grams per mole, or a mole of carbon is 12.01 grams. So if I have grams and I want to get to moles, it is the molar mass that I use as my conversion factor, are going backwards as well. We also use Avogadro's number, never usually here too much, but occasionally it does pop up. But Avogadro's number, which is used to go from moles to molecules or atoms, right? That's your 6.022 times 10 to the 23 atoms is equal to 1 mole. That's your Avogadro's number. That is the conversion factor to go from moles to atoms or molecules or back along the way. So if you have grams, you're going to divide by the molar mass to get moles. Those will cancel. If you have moles and you want grams, you're going to multiply by the molar mass. Those will cancel, and that will get you grams. So that's a conversion we do a lot, especially in labs, figure out how many grams you need to weigh out and things like that. So using the molar mass. We have a compound or something like that, you just add up all the parts, right? So you go to periodic table, 2 hydrogens at 1.008 plus 1 oxygen at 16 grams, and you would basically add that up. Another really important sort of calculation is molarity, which is big M. Molarity is moles of solute per liter solution. That is rearrangeable. Liters is equal to moles divided by the molarity. Moles is equal to liters times the molarity. When you have a number that is in molarity, you should convert it out of molarity so you can see both of the units, 4.5 moles per liter. I say that because when people leave the big M, they have no idea what they're doing most of the time. They think they're doing like moles only. They don't even know there's liters involved or anything like that or where the volume is. So the number always stays with the moles. It's always per 1 liter. If you have the molarity and you have the volume, you should be multiplying that by the volume in liters. If you take milliliters and you multiply it by molarity, do you get moles? You do not get moles. You get what are known as millimoles, which are like moles, but about 1,000 times off what you're thinking the number is. So if you take milliliters times molarity, you get millimoles. You do need to, if you're using molarity by itself, you need to multiply it by liters to get moles, because that's most likely what you're going to want to use. Now, if you take millimoles and then divide it by milliliters, the millis cancel, and that does bring you back to molarity. So it's okay if you kind of do milliliters instead of liters with it as well. So it's really important to know how to calculate the concentration, and from the concentration, be able to get the moles. Make sure it is again in the proper units there for liters to do that. Probably also super important is everybody's favorite thing known as a dilution. Yeah. And that is an M1 V1 equals M2 V2 situation. Or nowadays they like to teach C1 V1 equals C2 V2, I suppose. And M is molarity volume, that's before the dilution. That is after the dilution. This is the same thing. This is before, this is after. The only difference is this is just generic for concentration. So most of the time people use molarity, so that's why we use the M1 V1 equals M2 V2 most of the time. But you could technically use some type of other concentration unit like percent mass to mass, percent mass to volume, whatever it may be. But most of the time we kind of use molarity. This is important. For example, let's say I was going to take some iron 3 and I'm going to use a stock concentration of 0.2 molar. And let's just say I had some thiocyanate and it was 1.5 molar as well. And let's just say I threw some deionized water in there. And for my first test tube, I used 10 milliliters of it, 5 milliliters, and we'll do 5 milliliters of that. So when I put it in there, my iron, my 10 milliliters, and my 5 milliliters of my SCN minus, and my 5 milliliters of my water, basically, is the concentration of iron in this mixture. Is it still 0.2 molar? It is not, by the way, right? So once you do that, you're actually doing a dilution. And if you want the actual correct concentration in it, you actually have to use the dilution equation here. So if I want to know what my iron's concentration would be, I would have to take the stock solution concentration, times it by the volume. That would be my M1 V1. My M2 is what I'm looking for. My V2 would be my total volume that went in there as I mix it all together. That's a grand total of 20 milliliters here, right? So when I do it for this particular one, that's 0.2 times 10 divided by 20. That gives me an M2 of 0.1 molar. Remember, molarity is moles per liter of solution. So as you continue to add solutions into the same container, the molarity consistently changes, but the moles stay the same. So a lot of times people, and that's a very common thing in lab, you have to be able to calculate the correct concentration. And most of the time, if you're mixing a bunch of solutions together, you're doing a dilution, you would have to do that for everybody. So if I wanted this guy's concentration, I would have to do a similar calculation for it to know what his concentration is in that mixture. So that's really, really important. So just to close up, concentration, molarity, dilutions, being able to write equations, double displacement reactions, calculating grams from molar mass. These are things from Chem 50 that do pop up a lot here in Chem 51. So you want to make sure that you have a handle on that. Any questions? All right.